All right, so let's put together the acceleration in the rotating frame with the pressure force, the force of gravity, and the viscous forces, and write down what the momentum equations or equations of motion are for the ocean. So remember from the last lecture we derived that the acceleration as viewed in an inertial frame, dt, in the inertial frame, which is what we can apply, this is the acceleration in the F equals ma, right? Mass times this would be equal to the forces. So if I put in a row here, this would be the mass per unit volume times the acceleration in the inertial frame would be equal to the forces. Right, so this would equal to the forces. And this can be written in the rotating coordinate frames as rho times dv in the rotating frame, right? The acceleration as viewed in the rotating frame, the acceleration in the rotating frame of the velocity in the rotating frame, plus 2 times omega, the rotation vector for the Earth, crossed with the v in the rotating frame, plus omega cross omega cross r. So that's the acceleration as viewed in the inertial frame, expressed in terms of the velocity viewed in the rotating frame, or expressed in terms of the acceleration viewed from the rotating frame. This bit is going to give rise to what's called a Coriolis force. This bit is going to give rise to what's called a centrifugal force, and I just want to make a note about this term. This is one of the few examples that we don't have associativity, in that you cannot do omega cross omega first and then cross with r, because omega being parallel to itself would mean omega cross omega is 0, and 0 cross r would then give you 0. So it's important that you first do this part first, omega cross r, and then you take the result and you cross that with omega, so that you don't get 0. Okay, so now what are the forces, right? So we have a few forces that we've learned about already. The first one is the pressure force, which is minus the gradient of the pressure. The other one is the force of gravity, right? Plus F for gravity. And then we have those viscous forces from the unresolved small scale, so plus mu del squared of V in the rotating frame. Okay, so now I'm going to get rid of this. I'm going to keep everything in the rotating frame from now on. And so I'm going to get rid of the rotation symbol, but just to remember that from now on, the velocity is in the rotating frame, or a frame that's fixed relative to the Earth, which is spinning. So the V now is V rotation from now on, and is equal to U, V, and W, this being the eastward direction, northward, upward. So let me write that again. U, eastward component of V rot. V is the westward, so the northward, and W is the upward component. And we're going to just write V from now on. So this inertial business now is gone. So forget about this. We'll never use this again. We're always going to be in the rotating, in the frame that's fixed with the Earth. So the one that we're used to. Okay, so let's look at this term here. So this term, which is the centrifugal, is going to get lumped in with the force of gravity. So that force, if I write down a picture of the Earth like this, and this is the spin axis, and so omega, so if I pick a point here, omega is in this direction, and this is r, right? So if I do omega cross r, it's going to be into the board, right? Into the board, this is r, omega cross r points into the board, and then omega cross that result is going to be in this direction. So this direction here is going to be omega cross r. And if I bring it to the other side of the equal sign, then I'll have in this direction minus omega cross omega cross r. So this direction is minus omega cross r. Right, this is the equator, by the way. Okay, this is phi is the latitude. Now what we call the effect of gravity is going to be the vector sum of a force in this direction, Fg, which is the force of gravity, right? Fg here is minus gmm over r squared, where m is if we do it per unit volume, that would be rho. Right, so m is the mass of the Earth, and then rho is the density of the fluid. So that would be the force of gravity per unit volume. So it's not gmm, the mass of two body, but just rho, where rho is the density of the water. That is pointing towards the center of the Earth, right? So if I do the vector sum of these two, I'm going to get a vector which is not pointing towards the center of the Earth. It's going to be off to the side a little bit. And that direction is in the minus z hat direction. So if this is z hat, which is pointing upwards, this will be in a negative z hat direction. And so what happens is that because the Earth is spinning, the shape of the Earth becomes an ellipsoid or a spheroid. And my picture is getting messy, but I want to make it a little bit fatter. Something like this. And this direction here is opposite direction of the vector sum of the centrifugal and gravity. Minus omega cross r is equal to minus the gradient of rho g z. Actually, I could take the rho outside the gradient here. Minus rho grad g. I can take the g out. G is a constant also. G grad z. So this is the rho gz, right? That's the gravitational potential, but it includes the effect of the rotation of the Earth, the centrifugal force, so that it's in the z direction, where z is not pointing radially outward, but is in the direction perpendicular to a surface of constant geopotential. Okay, so if I do this this combination of these two together, and I define z to be perpendicular to, or anti-parallel to, the vector sum of centrifugal and gravity, then I can lump them together. I guess what I also want to point out is that, when we're rotating, right, we're doing a circle, there has to be an acceleration that keeps us going in a circle, right? Because when we stay on the Earth. And that force is the centripetal force, which is the force directed towards the axis of rotation. That centrifugal force comes from gravity. So gravity keeps us fixed to the Earth, right? When we're standing, if we were standing at the equator, we don't just fly off the surface of the Earth. The force of gravity, which is in the opposite of that centrifugal, keeps us to the center of the Earth. And it's easy to see at the equator that the force of gravity, which is directed in this direction, and centrifugal, which is outward, the force of gravity is so much bigger than the centrifugal that we can just subtract a little bit of the force of gravity to give us the centripetal to cancel off the centrifugal, and we're going to stay on the surface of the Earth. As we go northward, we can just take the projection of the force of gravity, right, onto this direction here for the centrifugal, and there's going to be a small part of the force of gravity, the component in this direction towards the axis, and that will balance off the centrifugal force, or keep us moving, going in a circle. And we can project. Now, when we reach the North Pole, then the force of gravity, right, is perpendicular to omega cross r. And so then the force of gravity cannot cancel that vector, but fortunately, omega cross r vanishes at the North Pole, because at the North Pole, omega and r are parallel. And so this vanishes, and so this whole term vanishes, and so there is no centrifugal at the North Pole. And so even though gravity is perpendicular to the centrifugal, it doesn't need to provide a centripetal force to keep us moving in a circle. All right, enough talking about this. Let's write down the equations. So now, these equations will become rho dv rotation, or I'm going to take out the rotation now, dt plus 2 omega cross v is equal to minus grad p minus grad of rho gz. That's the force or the gravitational acceleration that comes from the combination of this and this, plus the viscous force, mu del squared v. And if I divide through by rho, which I'll do in the next line, I get dv dt plus 2 omega cross v is equal to minus 1 over rho grad p minus grad gz plus mu del 1 over rho del squared v. And now I can write this down in component form, right? The u component, the v component, and the w component. But to do that, I need to figure out what this 2 omega cross v is in each of the components. So the omega vector, where can I write? I can erase up here. Make my little picture here. I'll put down the Earth like this. The vector omega is in this direction. I pick a point on the surface of the Earth over here, and I define this way in the y hat direction. This one is in the z hat, directly upward, and the x hat is into the board. So now I'm going to take out the different components of omega. And so the part of omega that projects into the x direction is going to be 0, right? Because omega is parallel to the x-axis. Is parallel to the spin axis, or is the spin axis, and that is perpendicular to the x-axis, which is in the board. So we get 0 in the x direction. In the y direction, right, omega is going, this is the latitude phi, right? Omega is up here. It will be omega cosine of phi, right? So at the equator, right, then northward is directly in the direction of omega. So we get the full bang from the Coriolis, from the spin component. And now the part that projects onto the northward direction, it's going to be parallel to the z-axis when we're at the North Pole. So this will be omega sine of phi, right? At the North Pole, the latitude is pi by 2, sine of phi is 1, so we get omega. And at the equator, this term vanishes, but we have everything being in the northward direction. Okay, so that's what the omega is. So now we can calculate what this 2 omega cross v is. So omega cross v, like this thing here, we can compute that using the determinant rule, x hat, y hat, z hat. Then we put the 3 components of omega, which is 0, omega cos phi, omega sine phi. And then we put the 3 components of v, which is u, v, and w. And then we compute what would be the determinant is x hat times this minus this times this, which is omega times w cos phi minus v sine phi plus y hat, or minus y hat. Right, we go plus minus y hat times this minus this times this. So minus u omega sine phi. So minus omega u sine phi. And then plus z hat times z hat is this times this minus this times this. U cos phi. So we have the 3 components here of this quantity, which are just, if I can write this one a little bit smaller here, plus omega sine phi So I took what was the minus and I combined with the minus and I put a plus. And so the three components are omega W cos phi minus V sine phi. Omega times W cos phi minus V sine phi. That's the x-hat component. Omega sine phi. Oh, and I already forgot the U. Times U. And I rewrote it. And then the minus omega times U. Omega cos phi times U. I don't know if you can see very well. Let me rewrite. I'm going to erase this and I'm going to copy that right here. And write it big enough so you can see. Alright, so these are the three components of omega cross V, these three here. And so now we have what we need. We know what this is in component form. We can compute what all the other ones are in component form and write down the three components of the equations of motion, which I want to write down in their full glory here, just above, so because I have no space everywhere else. Okay, so let's start off by writing the x component, or the eastward component of dv dt. So this, remember, is the material derivative. So du dt, u is the x component of v, plus v dot grad u. So that takes care of this material derivative. And now we have this term, which is plus 2 omega times w cos phi minus v sine phi is equal to minus 1 over rho, and the x component of this is just dp dx, minus this one, the x component of this is 0, right? The gradient of z, d by dx of z is 0, so this one vanishes, no gravity in the x direction, plus mu over rho d2 u dx squared plus d2u dy squared plus d2u dz squared. So these are the viscous terms. So the diffusion of momentum, of eastward component of momentum. And this one, v dot grad u, I can expand this one also. So it's going to be, one more time, du dt plus, so v is u, and grad u is du dx, du dy, du dz. So u du dx plus v du dy plus w du dz plus 2 omega w cos phi minus v sine phi minus 1 over rho, equals minus 1 over, equals minus 1 over rho dp dx plus mu over rho, this business, del squared of u. I'll go back to the del squared after I've expanded out. Okay, so that's the x component of this equation. The y component will be very similar, except u will be now v's, dv dt plus v du d, plus, this is still u, but this is v, dv dx plus v dv dy plus w dv dz plus 2 omega and u sine phi. U sine phi, that's the y component of the Coriolis, the y component of this business, is equal to minus 1 over rho dp dy plus mu over rho del squared v. And then we have the w component. The w component will be almost the same, except now we'll have to keep the gravity, right? This time the d by dz of gz will give me a minus g. So, because I have to erase this here. So I'm going to erase this. And now we can write the final one, dw dt plus u dw dx plus v dw dy plus w dw dz plus 2 omega u cos phi, but with a minus. Right, there's a minus. Is equal to minus 1 over rho dp dz. And then the force of gravity, which was 0 in those components, is no longer 0, minus g. And plus mu over rho del squared of w. Alright, so we have the three equations. So let me erase all the stuff that doesn't belong. This one. So here we have written out in all their glory the three components of the momentum equation. The first part is the material derivative of the velocity, right? Or the substantial derivative sometimes it's called. Then over here we have the Coriolis force. And the first part here, that's the pressure force. This is gravity, which appears only in the vertical, in the W component, right? And then we have the viscous stresses, the viscous forces. All right, so there's some approximations that are usually made for the Coriolis force. So if we look at the first term, there's this W cos phi minus V sine phi. So in the ocean, because the ocean is very, the length scales are very broad in the horizontal directions, but fairly restricted in the vertical. So the deepest point in the ocean is maybe 10 kilometers, but 10 kilometers is not very big compared to the tens of thousands of kilometers of the horizontal extent of the ocean. And so this term is very small compared to that one. And so this one is usually neglected. So this is small and compared to V sine phi, and therefore neglected. So what we're left with is minus 2 omega sine phi times V. So 2 omega sine phi, if we're in the northern hemisphere, sine phi is going to be positive, 2 omega sine phi is positive. If V is positive, suppose that we have a northward velocity, then this would be minus some positive number. So if I bring it to the S side, this would be positive, which would mean U would get a positive acceleration due to the Coriolis force. So if I'm moving north, there'll be an acceleration in the positive x direction or in the eastward direction, right? So if we're moving north, we get deflected to the right, which is what we're usually used to. Okay, so that term gets neglected for the motions in the ocean. Of course, this term will not be negligible for other problems of mechanics. For example, if you were to drop a penny in a well, in a very deep well, then the penny will accelerate because of gravity as it falls down, and at some point its speed will be very high, and then this term may become important, and so now you will get a deflection, right? So we calculate which way the deflection will be. So W, which is accelerating, or which is going downwards, is going to be negative. So this whole term here will be negative. If I put it over to this side, it will become positive. So we would get an eastward acceleration. So if you're to drop a penny in the well, because of the rotation of the Earth, it would get deflected eastward, right? So that's from this term. But in the ocean, this first term is negligible. All right, then this one is the other component of the Coriolis force. This one, if we're moving eastward, right, this whole term is going to be positive. We bring it on this side, it becomes negative, which would lead an acceleration in the negative y direction, which would be southward. So if we're moving eastward, we're going to get deflected southward, right? Southward, which is what we're usually used to the right from the direction of motion. And then we have this, the vertical equation. So there's also a Coriolis force in that one. And this one, we also neglect this one. So this is traditionally negligible, neglected. But the justification for this is not as good, so it depends on the problem. So it's true that this term is tiny compared to G, right? G is of order 10, and 2 omega cos phi is of order 10 to the minus 4. So if U is of order in the ocean of 10 cent, well, let's say 1 meter, we're in the Gulf Stream. So a very fast current would be of order 1 meter per second. This whole term is of order 10 to the minus 4, whereas this is of order 10. So this one is about 5 orders of magnitude smaller than the force of gravity. And so you might think that you can neglect it, which is true to first order, but what should be really comparing is comparing this to the imbalance between these two terms. So if we're doing a non-hydrostatic problem, what's important will be the magnitude of this relative to the imbalance between these two terms, because there's almost perfect cancellation between the pressure and gravity from this hydrostatic balance. And so whether or not this is negligible depends on the problem. Okay, so embedded in these equations are various balances that we think about in oceanography, and one of them is precisely the balance between these two terms, the gravitational acceleration balancing the pressure force. So gravity and pressure being balanced in the vertical, that's called the hydrostatic balance. So if 0 is equal to minus 1 over rho dp dz minus g, so in other words, if the acceleration terms, and this Coriolis term we always said is small, if this one is small and the viscous forces are small, then we get what's called a hydrostatic balance. Hydrostatic balance. And this balance is certainly very good on large scales in the ocean. So everything except for fairly small scales like breaking waves on the beach, that would be a counterexample where things are not hydrostatic, but if you're on scales of tens of kilometers, then in general the fluid motions will be in hydrostatic balance, and these two terms will balance each other. In other words, the pressure force, which goes from high to low pressure, which is pointing upwards, will balance the force of gravity, which is pulling you downwards. Okay, so that's in this z component of the momentum equation. We have embedded in there the hydrostatic balance in the limit where the acceleration and the viscous forces are small. Other interesting balances we have in these equations are in the horizontal equations. If the acceleration terms are small and we're left with the Coriolis forces balancing the pressure forces, then we have what's called the geostrophic balance. So if friction is small and the acceleration are small, then what we have is the geostrophic balance. So if 2 omega minus sine phi times v is equal to minus 1 over rho dp dx, and in the other equation, plus 2 omega sine phi times u is equal to minus 1 over rho dp dy, then we call this the geostrophic balance. And in the geostrophic, this parameter 2 omega sine phi appears in both equations, so we usually define a parameter called f, which is the Coriolis parameter, which is equal to 2 omega times the sine of the latitude, sine phi. And so at the equator, where phi is 0, sine phi vanishes, so the Coriolis parameter vanishes. And so we don't get a geostrophic balance close to the equator, but as soon as we move off the equator, maybe 2 degrees of latitude, already this balance becomes pretty good, and we have geostrophic balance on fairly large scales again. On scales, I guess here the scale for a geostrophic balance will depend on the other terms being negligible, and so it's a question of spatial scales, and usually by the time you reach tens of kilometers, maybe hundreds of kilometers, for sure, things will be in geostrophic balance. So that's why if you move a few degrees off the equator, then the Coriolis force becomes important, even though sine phi is still small. And then at the North Pole, then this is definitely an important balance in the ocean. Other balances we have in the equation are, we're going to see later, is going to be a balance between the Coriolis and the viscous stress. So if we include the Coriolis force, the viscous stress near the surface, and we make sure that the viscous stress matches the stress implied at the surface from the wind, then we will get what's called an Ekman balance. So the Ekman balance will include Coriolis and the viscous stress. These will be the main balance in the interior of the fluid, and when we reach right at the surface of the ocean, then this stress will have to match the stress due to the wind. And so in this term and this term, as well as this term and this term, that is going to give us what's called the Ekman balance. Another interesting balance that we have for motions in the ocean is one where none of the forces are important, where we just have with the acceleration. So if I just have, and the Coriolis force, so if I have du dt, the acceleration, and we neglect the nonlinear terms, plus 2 omega, well, I'll just call it f, minus f times v equals 0, and in the other equation, dv dt plus f times u, right, it's u in this one, equals 0. These two equations, I can combine them, right? If I take d by dt of the first one, what I get is d2u dt squared minus f dv dt equals 0, and dv dt is just minus f times u, so this becomes d2u dt squared plus f squared u equals 0, right? So I've taken the t derivative of this one, I get this, and then where I see dv dt, I substituted with minus f times u. Now I have one differential equation in u alone, and this equation is easy to solve. The equations are going to be of the form u is equal to a e to the f times t I plus b e to the minus I f times t. In other words, these are oscillating functions, right? And they are rotating. So these will define what are called inertial oscillations. So if you put a current meter in the oceans, you'll see all these oscillations in the currents at a frequency f, where f is 2 omega times the sine of the latitude. So depending what latitude you are, the period of these waves will change, but it'll be on the order of 2 cycles per day. And those are called inertial oscillations, where there's no force, just the force of inertia. And it's because we're on the rotating frame that we see these balances. I think these are all the balances, the main balance I want to point out. Oh, there'll be another one that we'll talk about where we include both the geostrophic balance, right, pressure balance Coriolis in the horizontal equation, and we combine that with the hydrostatic in the vertical. And if we combine those two balances, we get what's called the thermal wind balance.